Now we're going to spend a little bit of time talking about properties of chords. First off, remember that chord in a circle is when a segment connects 2 points on the circle. So we have a point here and a point here. And so this right here is a chord. And so we have congruent central angles. If we have congruent central angles, this angle is congruent to this angle. Then we talked last time that the arc measures would be the same. Also the same is that the chords are congruent. And so all of these are interrelated. So if you have congruent central angles, you have congruent arc measures. This arc and this arc. And you also have congruent chords. We're talking about within the same circle because, as we talked about last time, if we have congruent central angles but we have a bigger circle that we're talking about, the arc measure is not the same. But all of these are interconnected. If and only if and only if and only if. Back and forth. So what this could look like, in this picture, we've been given that AC is 8 and AT is 8, so this chord is congruent to this chord. So if that's true, then this arc must be congruent to this arc. So if I wanted to find, say, measure of arc AC, well, I know that this arc is 160, and so if I went all the way around, that arc would be 360 minus 160, and so I call this the leftovers. This is 200 degrees. So if that's 200, and those two arcs are congruent, then 200 divided by 2 must be what we get, because they're equal. So this plus this, if you call it x, so you could say x and x, x plus x is 200, so 2x is 200. Either way you want to look at it. So you get 100 degrees for arc AC. And it'd be 100 degrees for arc AT as well. So next, what we want to talk about is if we have a chord that just happens to not only be perpendicular, but it also bisects, then this chord has to be the diameter. There's no other way. It's always true. And how you can get there is you can easily draw in this circle, this radius, and it's proven pretty quick with the radius and the radius that these two triangles are congruent by HL. And so we can do that formally in class if you want. But so what's cool about that is that anytime you have the perpendicular bisector of a chord, it's on the diameter. So say you planted some trees, and you wanted to water those trees, and so you wanted to know where to put the sprinkler so that it would hit all the trees. In other words, the center of the circle. And so if you make a line from one tree to the other, and you perpendicularly bisect that, and you make another line from your second tree to your third tree, and you perpendicularly bisect that. Both of these perpendicular bisectors have to be a diameter, and so where the diameters intersect, this is the center of your circle, and where you should put your sprinkler if you want to hit all three trees at the same time and maximize your water usage. So anytime you have a perpendicular bisector of a chord, then the chord that perpendicularly bisects it has to be the diameter. Next, if you have a diameter that is perpendicular to a chord, this is the exact opposite if you notice, then it has to bisect the chord. So what this might look like is, it's kind of boring, but it's just to illustrate the point. If this is the diameter and it's going through the center here, if it's perpendicular to this chord, this 6 has to translate over here. It has to be bisected as well because it's perpendicular to the diameter. So that has to be 6. You can also use this in triangles and use the radius and things like that. Also, if we have congruent chords, we talked earlier about if we had congruent chords, then we would have congruent central angles and congruent arc measures. But here I want to talk about how if we have congruent chords, they are the same distance from the center. And so if you draw the line, draw the distance from the center to your chord, and remember to measure distance, we always go perpendicular. And so that distance and that distance is the same. Now I drew the double-headed arrow here because it goes both directions. If I know that chords are equidistant from the center, then I know the chords are congruent. And so using some numbers here and an example problem, since this is 12 and this is 12, and I've got these distances marked perpendicular, I know these are distances. So I could say, hey, they're equidistant. So 3x must be equal to 5x minus 7. So if I subtract 2x, sorry, I'm already subtracting and getting 2. So if I subtract 5x, some of you may wish to subtract the 3 over and add the 7 over, that's fine. So I get negative 2x equals negative 7. If I then divide by negative 2, I get x equals 3.5, 3.5, or 7 halves if you will. And so we can find x. If it asked us to find the length of that, we could plug it back in and find the length of that. But there you have it. That's what you get with chords inside of circles. And what congruent chords and congruent arcs and all that will get you. Just finding more missing pieces inside the circle.